Welcome to the solutions to the college physics springs and simple harmonic motion problem set, problems numbers 1 through 4. Let's go ahead, jump in and get started here. Number 1, a 0.40 kilogram object is attached to a spring with a spring constant of 160 newtons per meter, so that the object is allowed to move on a horizontal frictionless surface. The object is released from rest when the spring is compressed, 0.15 meters. Find the force on the object when released, and B, its acceleration at that instant. To calculate the force, we're simply going to apply F equals kx. Making our substitution, our spring constant was given as 160 newtons per meter. And our stretch, in this case it was compressed. Our compression from equilibrium was 0.15 meters. Doing our calculation, we get 24 newtons. They gave us the mass, so to find the acceleration, we're simply going to apply F equals ma. Our force of 24 newtons equals 0.40 kilograms times the acceleration. Divide both sides by 0.4, and we should get an acceleration 60 meters per second squared. Number 2, a small ball is set in horizontal motion by rolling it with a speed of 3 meters per second across a room, 12 meters long between two walls. Assume the collisions made with each wall are perfectly elastic and perpendicular to the two walls. A. Show that the motion is periodic and determine its period. B. Is the motion simple harmonic? Explain. Well, in the case of A, the motion is periodic since the motion repeats over and over, with the ball going back and forth between the walls with no energy lost in the process. Half of the period of the motion is the time for the ball to travel between the walls, since period is starting at one end and returning to that same spot. So if this side represents one wall, the ball travels across, hits, and comes back. That's one complete period of one cycle or oscillation, however you want to look at it. So half the period is the time for the ball to get from one wall to the other. Well, the walls are 12 meters apart, and simply applying the velocity equals distance over time formula. The time would be the distance divided by the velocity. The distance between the walls is 12 meters. The speed the ball is traveling is 3 meters per second. And dividing 12 by 3, we get 4 seconds. So if it's 4 seconds from one wall over to the other, it would take 4 seconds to get back. So the complete period is 8 seconds. Is the motion simple harmonic? The answer is no. The motion is not simple harmonic since the force acting on the ball is not in the form F equals kx. In fact, here, F equals 0 everywhere except when the ball is in contact with the walls. And then force, of course, is changing in the opposite direction. So there's no one spot where you would say the ball would be at equilibrium. Okay, that's another good indication that the motion is not simple harmonic. Okay, on to number 3. A child's toy consists of a piece of plastic attached to a spring as pictured below. The spring is compressed against the floor a distance 2 centimeters and the toy is released. If the toy has a mass of 100 grams and rises to a height of 60 centimeters, find the spring constant of the spring. All right, clearly what we have going on here is a conservation of energy. When the toy is, and this is often referred to as a pop-up toy, when the pop-up toy is compressed, it has elastic potential energy stored in the spring initially. It's not moving, and it has not gained a height in a gravitational field because it's right on the ground. In the final state, the spring is no longer stretched or compressed. It's returned to its equilibrium, so no elastic potential. At its maximum height, it's stopped, so no kinetic. Has it gained a height in a gravitational field? Yes. So our conservation of energy statement becomes US equals UG. In equation form, that would be 1/2 K XO squared for elastic potential energy stored in the spring initially equals the MGH, gravitational potential energy, gained at the end of the event. We go ahead and substitute. There is no canceling we can do here. 1/2 K, 0.02 meters was the compression here. It's in centimeters. We have to convert that to meters. Equals M, 0.100 kilograms, G, 9.81 meters per second squared. H was given as 60 centimeters, which is 0.600 meters. Do the algebra and solve for K, and we get 2,940 newtons per meter. Number 4, a 10-gram bullet is fired into and embeds itself in a 2-kilogram block attached to a spring with a spring constant of 19.6 newtons per meter and whose mass is negligible. For the record, they always will do this, and they're called light springs. So if you ever hear that term used, light spring, what they're doing is negating the mass of the spring so you don't have to consider it in the calculation. How far does the spring compress? If the bullet has a speed of 300 meters per second at the moment of impact of the block, and the block slides on a frictionless surface. Well, just by the nature of the description of this problem, this sounds pretty familiar. And it should sound familiar because we have a before and after diagram here, which is going to lead us to a conservation of momentum in order to get started. Before we get ahead there, let's take a look at our before and after diagram. We have a bullet at 300 meters per second. It's the only object moving. It hits, embeds inside, and compresses this spring a distance x that we're trying to find. In order to do that, what we need to know is how fast is the bullet block combo going just as the bullet embeds in the block and starts to compress the spring. Frictionless indicates to us that we'll solve that by using conservation of energy. But first, we have to know how fast the bullet block combo is going after collision, and to do that, we're going to conserve momentum. So here we go. What objects have momentum before is just the bullet. Its mass of 0.010 kilograms. That you had to get from the 10 grams up here, times 300 meters per second equals, well, they're stuck together, so we add the mass of the two together after, and looking for the final velocity after impact. Solve for V, and we get 1.493 meters per second. All right, just as mentioned a moment ago, now we're going to conserve mechanical energy to find the compression of the spring. The final velocity of impact becomes the initial velocity for the compression portion of the problem. And so we start off with this block and bullet together having kinetic energy, which gets transferred to potential energy stored in the spring as it compresses the spring. There's no height gained or lost here, so there is no gravitational potential energy in this problem. So again, our initial kinetic becomes our final elastic potential energy stored in the spring. Our equation for kinetic, 1/2 mvo squared equals 1/2 kx squared for elastic potential energy. Any canceling we can do? Yes. There's a half in both terms, so we can cancel that. Go ahead and make our substitution. We've got a combined mass of 2.01 kilograms moving at 1.493 meters per second. Don't forget to square. And we have our spring constant given above in the problem, 19.6 newtons per meter, times our compression squared. Go ahead and do the algebra. You'll have to take the square root after you divide, and you should get a compression of 0.478 meters. All right, that'll do it on the solutions for 1 through 4. More to come in class as we tackle number 5 together in class tomorrow.